If I take this piece of chalk and just open my fingers like this, it falls. Boom. It hits the floor and maybe breaks. You have seen this a million times. If the chalk suddenly hovered in the air or flew up to the ceiling, you would scream. You would think you had lost your mind. But when it flies down, you don't even blink. You remain calm. Why? If I ask you, why did it fall? You will look at me like I'm an idiot and say, because of gravity, of course. And that is where we make our main mistake. We confuse the name of a phenomenon with the understanding of it. My father often taught me this when I was a boy. We would walk in the woods, and he would say, "You see that bird? It's a brown-throated thrush. In Germany, it's called a Zen drossel. In China, Chungling. But even if you learn all the names of this bird in all the languages of the world, you will know absolutely nothing about the bird itself. You know nothing about why it sings, how it teaches its young to fly, where it goes in the winter. You only know what humans call it. With the word gravity, we are simply fooling ourselves. We slap a label on a mystery so we don't have to feel anxious about it. Because if you think about it, look at this properly. The chalk is here. The earth is there, down below. There is nothing between them. Empty space. The air doesn't count. It falls the same way in a vacuum. There are no ropes. There are no gears. The earth doesn't reach out a hand to grab this little piece of calcium. How does the earth know the chalk is here? How does the chalk know that there is a giant ball underneath it that it needs to fly toward? Does the chalk have eyes? Does it feel a call? The ancients said it was the love of matter. That like attracts like. Then Newton said it was a force acting instantly across the void. But even Newton, and he was a very smart guy, was terrified by this idea. The idea that one object can influence another without touching it, without any intermediary, that is magic, pure witchcraft. But we have gotten used to this witchcraft. We have built our whole lives on it. We feel weight. We feel the floor pushing against our souls, and our intuition, our everyday experience, tells us something very simple about forces. It says, if you want to move something heavy, you need to push hard. If it's something light, you can push gently. Force is effort. It is muscle tension. And it seems completely obvious that the earth, this giant machine, must work the same way. It must pull heavy things harder than light things. That sounds logical, right? A heavy stone should fall more powerfully and faster than a light pebble. For 2,000 years, people believed this because it was common sense. But nature couldn't care less about our common sense. And if we really look at how things fall, rather than how we think they fall, we will see something that completely contradicts our intuition. Let's perform a simple experiment, a thought experiment, because I'm too lazy to drag bricks in here. Imagine that in one hand I am holding a heavy cannonball, in the other a small wooden ball. The cannonball weighs, let's say, 100 times more than the wooden one. If I ask you with what force the earth pulls these objects, you will answer, of course, it pulls the cannonball harder. And you would be absolutely right. If I put the cannonball on your foot, you will feel it. The earth has really latched onto that ball with tremendous force. And the wooden ball, barely at all. And here is where our common sense falls into a trap. The ancient Greeks, very smart fellows, said, if the earth pulls the cannonball 100 times harder, then it must fall 100 times faster. Sounds logical, doesn't it? If you push a cart with all your might, it moves faster than if you push it with one finger. But then comes Galileo, climbing up a tower, or more likely, rolling balls down an inclined plane, and he shows us something that simply doesn't fit in our heads. He releases them simultaneously, and they hit the floor, simultaneously. Bam! One sound. How is that even possible? Listen, this is a real puzzle. On one hand, the earth pulls the cannonball with monstrous force. On the other hand, the wooden ball with barely any effort. And yet, they fly neck and neck, the whole way down. No one overtakes anyone. To understand this, we need to remember another thing, the laziness of matter. We physicists call this inertia. Imagine these two balls are lying on ice on a skating rink. There is no gravity, they are just lying there. You walk up to the wooden ball and give it a gentle kick. It rolls away. Easy. Now you walk up to the massive cannonball and try to kick it with the same force. What happens? You break your toe, and the cannonball barely budges. Why? Because mass has the property of resisting changes in motion. The heavier the object, the lazier it is. It is harder for it to speed up. And now look at the beautiful picture that emerges. Just magnificent. Look at the cannonball. The Earth says, "I will pull you hard." And the cannonball replies, "I don't care. I'm heavy. I'm hard to move." Look at the wooden ball. The Earth says, "Well, I'll pull you gently." And the ball replies, "And I don't need much. I'm light. I speed up instantly." And right here, a miracle happens. A mathematical miracle. The Earth's pulling force grows in exactly the same proportion as the object's inertia grows. If an object is 100 times heavier, the Earth pulls it 100 times harder. But it needs 100 times more force to accelerate, just like the light one. Nature has seemingly tweaked the settings. She perfectly balanced the pulling force and the resistance to motion. They cancel out. Mass disappears from the equation. It doesn't matter what you drop, a grand piano or a matchbox. The motion will be identical. But do you know what bothers me? What keeps me awake at night? It's this coincidence. We have two completely different characteristics. One is heaviness, how strongly the Earth wants to pull you. The other is inertia, how strongly you resist a kick. Why are they always the same? Why are there no objects that are very heavy on a scale but accelerate from a light flick? Or objects that are weightless but impossible to budge? In classical physics, we simply accepted this as a fact. We said, well, that's how the world is built. Inertial mass equals gravitational mass, period. But in science, if you find such a perfect coincidence, it usually means you are missing something. That you're looking at two sides of the same coin, but you don't see the coin itself. We found out that everything falls the same way. A stone, a cannonball, a feather, if you remove the air. But what if I told you that falling is not just what happens here in this room? What if I told you that the entire universe is engaged in one infinite fall? Look up. Look at the moon. It looks like it is peacefully hanging in the void. But in reality, right at this second, it is falling toward us. And the only reason it hasn't crashed onto our heads yet is that it keeps missing. Now let's expand our imagination. Let's move away from pebbles and cannonballs. Let's look up. For a long time, people looked at the sky and thought that completely different laws operated there. Here, down below, things are dirty, heavy, they fall, break, stop. But up there, perfect spheres, planets, the moon, they move forever in perfect circles. It seemed like two different worlds, the world of earth and the world of heaven. Isaac Newton was the man who broke down this wall. He had an amazing, audacious idea. He thought, what if the force that makes an apple fall on my head is the same force that keeps the moon up there? Sounds strange, right? The apple falls down to the ground. The moon doesn't fall on us. It circles. How can it be the same force? To understand this, let's conduct another thought experiment. Imagine we built a huge cannon on top of the highest mountain in the world, above the atmosphere, so the air doesn't bother us. We load the cannon and fire a ball parallel to the ground. What happens? The ball flies some distance in an arc and falls to the ground. Add more gunpowder, shoot harder. The ball flies faster, travels further, but eventually gravity bends its path, and it crashes into the ground again somewhere over the horizon. And now, and this is the moment where you need your imagination, imagine we fired with monstrous power. The ball is flying so fast that something interesting starts to happen. Look, the ball falls. Gravity pulls it down, toward the center of the planet. But while it falls down, it flies forward so fast that the Earth itself begins to drop away from under its feet. The Earth is round, after all. Its surface curves. If you pick the speed perfectly, magic happens. The ball falls 5 meters down, but during that time it travels forward so far that the surface of the Earth curves away exactly 5 meters down. The ball falls, but the ground runs away from it at the same speed. The distance to the surface doesn't change. The ball falls forever. It never touches the ground. It returns to hit you in the back of the head, having completed a full circle. This is an orbit. This is what the moon is doing right now. In this very second, The moon is falling toward the Earth. If we turned off its sideways motion, it would crash into us, and that would be a very bad day. If we turned off gravity, it would fly away in a straight line into the darkness of space. But the balance between its speed and its fall creates this eternal dance. The moon is just a rock that has been falling for billions of years and just can't seem to hit. Newton united the universe. He showed that there are no laws of heaven and laws of earth. Gravity is universal. Every particle of matter in the universe attracts every other particle. You attract the moon attracts you, your dog attracts Sirius. It is an infinite web of connections. Newton gave us a formula. He gave us a law that allows us to predict the motion of planets with incredible accuracy. We still use his equations to send rockets to Mars. They work magnificently. But there was one problem, one small but very annoying detail that tormented Newton himself until the end of his days. He knew how to calculate gravity, but he had no idea what it was. How does it work? How does the Earth yank the moon? There are 380,000 kilometers of emptiness between them. There is no rope, no chain, no gears. If the sun suddenly disappeared right now, would the Earth immediately fly out of orbit? Newton thought yes. That gravity acts instantly. But how can information that the sun has disappeared be transmitted instantly through nothing? This action at a distance seemed absurd. Nature doesn't like magic. There must be a mechanism. There must be something that transmits this influence. And we had to wait almost 300 years until a man working in a patent office in Bern looked out the window and asked perhaps the most important question in the history of physics, a question that turned everything upside down. Albert Einstein called this his happiest thought. Imagine, 1907, he's sitting in the patent office, bored, watching workers on the roof of a neighboring building, and suddenly a thought strikes him that seems almost childish. He thought, if a man falls from a roof, then during the fall, he will not feel his own weight. Sounds trivial, right? Oh, well, of course he doesn't feel weight. He's falling. But Einstein saw in this the key to the structure of the universe. To understand what he saw, I have to lock you in a box again. Imagine waking up in an elevator. It is a perfect elevator. No gaps, no windows, absolutely airtight. Outside is total silence. You are standing on the floor. You feel your weight. Your feet press against the floor. You take keys out of your pocket, release them, and they fall to the floor. Clink. What conclusion do you draw? You are a physicist. You trust your senses. You say, I am on Earth. Gravity is pulling me down. But what if I told you that you are wrong? What if there is actually no Earth underneath you? What if this elevator is in deep space, far from any stars or planets, and tied to the roof of the elevator is a cable pulling an alien spaceship? The ship accelerates. It pulls the elevator up with an acceleration of exactly 9.8 meters per second per second. What happens inside? The elevator floor catches up to your feet and presses against them. You feel weight. You release the keys. The keys hang weightless by inertia. But the elevator floor flies rapidly toward them and hits them. Clink. You see the same thing. You feel the same thing. No experiment inside this box will allow you to distinguish gravity from acceleration. They are not just similar. Einstein realized they are the same thing. Now let's do something scary. Let's cut the cable. The elevator starts to fall, or if we are in space, it just flies by inertia. What happens to you? The floor drops away from your feet. You float. You take out the keys, let go, and they hang right next to your face. You push them with a finger, and they float in a straight line until they hit the wall. You say, gravity has disappeared. But wait, if you are falling in an elevator on Earth, gravity hasn't gone anywhere. The Earth is still there, down below, huge and heavy. It is pulling you with all its might, but you don't feel it. This blows the mind if you think about it. Gravity is the only force that can be completely canceled simply by letting it do what it wants. If you surrender to it, if you stop resisting and just fall, it disappears. For you, it no longer exists. What you call the feeling of gravity when you sit on a chair right now, that is not actually gravity. That is the electrical forces of the atoms in the chair, pushing against your behind and preventing you from falling to the center of the earth. You don't feel the earth's attraction. You feel the floor stopping you from moving naturally. The natural state of matter is free fall. Einstein called this the equivalence principle. Acceleration and gravity are two sides of the same coin. And if that is so, it changes absolutely everything. Because if gravity is the same thing as motion with acceleration, then it must affect not just rocks and keys. It must affect things that have no mass at all. It must affect light itself. Let's go back to our elevator in space. We are being pulled up by that invisible alien ship. We are accelerating. We feel the floor pushing on our feet, just like on Earth. Now imagine that in the left wall of the elevator there is a tiny hole. And outside, someone aims a laser beam into that hole. The beam of light enters horizontally, parallel to the floor. What happens? You say, light travels in a straight line. It will hit the opposite wall at exactly the same height it entered. But don't forget, we are moving. We are accelerating. Light is incredibly fast. But it is not instantaneous. It needs time, even a tiny fraction of a second, to fly from the left wall to the right one. And in that tiny fraction of a second, our elevator will manage to travel up a little bit. The floor will rise, the walls will rise. What does this mean for us inside? We will see the beam enter the hole, but hit the opposite wall just a little bit lower. The entry point is higher, the exit point is lower. If we trace the path of the beam inside the cabin, it won't be a straight line. It will be an arc. It will curve downward toward the floor. You say, well, that's just a trick. The light is actually straight. It's us who moved up. But remember what we agreed on 5 minutes ago? The equivalence principle. Everything that happens in an accelerating elevator must happen in a gravitational field too. You cannot tell one from the other. The laws of physics are the same. If acceleration curves a beam of light, then gravity also must curve it. And here we hit a wall, a brick wall of classical physics. Because Newton told us, gravity is a force that acts on mass. The greater the mass, the stronger the attraction. But light has no mass. A photon weighs nothing. If you plug 0 into Newton's formula, you get 0. Gravity shouldn't touch light. Light should be untouchable. It should fly through gravity like a needle through fog, not deviating by a millimeter. So who is right? Our thought experiment with the elevator, which says light must bend, or the great Isaac Newton, who says light doesn't give a damn about gravity? Einstein bet on the elevator. He said, if facts contradict the theory, you need to change the theory. Gravity really does curve light. And when we look at distant stars during a solar eclipse, we see that their light, passing by the sun, really does shift. The sun acts like a giant lens. But how? How can you pull something that weighs nothing? How can you grab something that is impossible to grip? The answer Einstein arrived at is so simple, and at the same time so insane, that it is hard to believe the first time. Gravity doesn't pull light. Gravity doesn't pull anything at all. Light isn't trying to turn. It is trying with all its might to fly in a straight line. It is the most stubborn traveler in the universe. But if light flies straight and we see an arc, it means the ruler itself, with which we measure straightness, has curved. It means the space itself through which the light flies is no longer flat. We have arrived at an idea that changes the very concept of place. Gravity is not a force, it is geometry. Let's forget about physics for a minute and talk about geometry. Imagine two tiny bugs living on the surface of a huge sphere. But there is one condition. These bugs are two-dimensional creatures. They have no idea what up or down is. They only know forward, backward, left, and right. To them, their world, this sphere, seems like an absolutely flat plane. Let's put these two bugs on the equator, some distance apart, and let's give them a command. Go strictly north. Go in a straight line. Do not turn. They start their journey. They walk parallel to each other. Their trajectories are perfect straight lines, perpendicular to the equator. In a flat world, two parallel lines never intersect. They should remain at the same distance forever. But as the bugs crawl north, something strange happens. The distance between them begins to shrink. They don't feel it. They didn't turn the steering wheel. They honestly moved their little legs strictly forward. But at some point, at the North Pole, they crash into each other. Imagine their dialogue. The first bug says, "Hey, why did you turn toward me? You pushed me." The second replies, "I didn't turn. I walked straight. Some mysterious force attracted us to each other." They will call it bug gravity. They will invent a formula that describes how this force grows as they approach the pole. But you and I, looking at this sphere from the outside, from the third dimension, know the truth. There was no force at all. They were simply trying to walk in a straight line on a curved surface. And on a sphere, straight lines, we call them geodesics, behave differently than on a plane. They converge. Einstein said, "We are those bugs. Only our sphere is not the surface of a planet. Our sphere is the very fabric of space and time. Massive objects like the Earth or the Sun do not attract other bodies. They do something trickier. They curve the geometry around themselves. When you throw a stone and it flies in an arc to the ground, it doesn't want to fall. It is trying to fly in a straight line in four-dimensional space-time. It is honestly looking for the shortest path from point A to point B. But because the Earth has dented space with its mass, that straight line looks to us like a parabola crashing into the dirt. It is hard to imagine because our brain doesn't know how to see in four dimensions. But the essence is this. Earth isn't pulling you down. Earth just dug a hole in space that you are sliding into. Or to be more precise, Earth curved the arena where the action takes place. Previously we thought space was an empty stage. Actors, planets, run around on it. The stage remains motionless. Einstein showed that the stage is also an actor. When a heavy actor walks onto the stage, the floorboards sag under him, and other actors involuntarily roll toward him. This explains why light bends. Light goes straight, but straight now means along the curve. This explains why all objects fall with the same acceleration. Remember our first question? Why do the heavy cannonball and the light ball fall in sync? Because it is not a question of weight. It is a question of the road. If there is a sharp turn in the road, both a Ferrari and an old truck must turn to stay on the track. The curvature of the road is the same for everyone. The curvature of space around the Earth is the same for the hammer and for the feather. They simply have nowhere else to go but to follow the curve. But there is one detail here that usually slips away. When I say space-time, you nod, but you are most likely thinking only about space, about pits, about hills. However, if you calculate honestly, the curvature of space alone is negligible. It is not enough to make a stone fall on your foot so quickly. The Earth is not heavy enough to bend space that much. The main trick of gravity is not that it bends space. The main trick is that it bends time. Here we come to the strangest part of this story. I told you that mass curves space-time. But let's be honest. Earth is a speck of dust in the universe. Its mass is too small to noticeably curve space. If gravity depended only on the curvature of space, you would fall to the floor not in half a second, but in hours. Space is very rigid. It is hard to bend. But time is a completely different matter. Einstein realized that gravity affects time much more strongly than space. The closer you are to a massive object, the slower time flows there. Down below, near the surface of the Earth, clocks tick just a tiny bit slower than up above, in space. Sounds like philosophical nonsense, right? Time slows down. But this is not a metaphor. It is a physical fact. If you take super precise atomic clocks and put one on the floor and the other on the table, then in 1 billion years, the clock on the floor will lag behind the clock on the table by a couple of seconds. Do you live on the first floor? Congratulations, you are aging 1/1000th of a nanosecond, slower than your neighbor in the penthouse. So what? You ask. What does this tiny difference in time have to do with me falling off a chair? Everything. It is crucial. Imagine a tank, or a lawnmower. It has 2 tracks. If the right track moves fast, and the left one hits mud and starts moving slowly, what happens to the tank? It starts to turn. It turns toward the slow track. You are that tank. You are moving through time. Always, every second. You are flying into the future. But your body is not a point. You have a head and feet, and because time at your feet flows a tiny bit slower, that's the mud, and time at your head a tiny bit faster, that's the asphalt, your movement through time curves. You start to pivot. Your future is no longer in front of you. Your future tilts geometrically downward, toward the center of the earth. You fall not because you are being pulled. You fall because the lower part of your existence moves through time slower than the upper part, and this skew forces your trajectory to bend toward the ground. Nature doesn't like to waste energy. She always looks for the path where time flows slowest. We call this the principle of least action. The stone flies to the ground because time passes more quietly there. It literally strives to go where it can age more slowly. This seems like madness until you look at your smartphone. GPS. The GPS system works thanks to satellites flying high above the Earth. Gravity is weaker there. That means time flows faster there than down here. How much faster? By 38 microseconds a day. Seems like nothing. But for navigation, where light travels 300 meters in a microsecond, this error is fatal. If engineers didn't program an Einstein correction into the satellites, artificially slowing down their clocks, then by tomorrow your navigator would show that you are driving not on the road, but through the neighboring forest. And the day after tomorrow, the error would be kilometers. Every time your phone accurately shows your location, it proves Einstein was right. Time is flexible. Gravity is the curvature of time. We have built an incredible picture of the world. We started with a falling stone and ended with bending time. We replaced force with geometry. We can calculate the trajectory of Mercury, the behavior of black holes, the expansion of the universe. We have created the most precise theory in human history. And here you sit, listening to me, thinking, well, now I finally understand everything. But I have to disappoint you, because if you ask me the simplest, most childish question, I will be forced to admit defeat. We know how it happens. We can write equations that predict everything to the 10th decimal place. But we still don't know why. You know, there is one thing that keeps me up at night. We just spent 45 minutes destroying old ideas and building new ones. We threw out Newton's force and replaced it with Einstein's curvature. We painted a beautiful picture, the fabric of space-time, geodesic lines, time dilation. It all adds up. The math works perfectly. And you might be tempted to say, well, now we know what gravity is. But let's be honest with each other. We don't. We just found a more accurate way to describe what we see. If you ask me, okay, space curves, but why? What is the mechanism? What exactly inside an atom tells the empty space around it that it needs to bend? If you ask that question, I will look you in the eye and answer, I don't know. And no one knows. You see, in science, we often confuse description with explanation. Imagine the astronomers of the ancient Maya. They had amazing mathematics. They could predict eclipses to the minute. They knew where Venus would be in 100 years. Their formulas worked. But if you ask them why, they would answer, because the sun god is at war with the moon god. Their predictions were correct. Their explanation was a myth. Are we any different? We replace gods with curvature tensors. Our predictions are more accurate. But do we know the true nature of reality? Gravity remains an outcast in the family of physics. We know 4 fundamental forces: electromagnetism, strong and weak nuclear interactions. They all live by the laws of quantum mechanics. We know there are carrier particles there, little postmen running back and forth delivering interactions. Photons, gluons, but gravity? It is a proud loner. It refuses to play by quantum rules. If we try to apply the equations of quantum mechanics to gravity, the math breaks. It spits out infinities. The results become meaningless. In the world of atoms, everything jiggles. Everything is uncertain. Everything jumps. In Einstein's world, space is smooth as silk and predictable. These 2 theories are the best we have. And they hate each other. They cannot both be true at the same time. This means that somewhere deep down, at a level we cannot yet see, something else is hiding. Maybe space-time consists of some kind of pixels. Maybe the graviton exists after all. Or maybe gravity is not a fundamental force at all. but just a side effect of something else, like temperature is just the movement of molecules, we stand on the edge of the abyss of ignorance. And that is wonderful, because if we knew all the answers, science would stop. Newton thought he knew the truth. It turned out to be just an approximation. We think Einstein knows the truth, but I'm willing to bet that in 200 or 500 years, someone else will say, Einstein was a smart fellow, but he only saw part of the picture. We don't need to be ashamed that we don't know why. Nature is not obliged to be understandable to us. She is what she is. Our job is not to impose our fantasies on her, but to listen to her, to find the keys, to guess the patterns. And the most amazing thing is not that there is something we don't know. The most amazing thing is that we, a bunch of monkeys on a small planet, could understand so much at all, that we can write a few symbols on a blackboard, and these symbols describe how galaxies dance billions of light years away. This leads us to the final thought, to the reason why we do science at all. Not for power over nature, and not even for new gadgets, but for the very music that the universe plays. So, what are we left with? We started by dropping a stone, and following that stone, we destroyed the concept of force, stopped time, and curved space. We found out that the dance of a dust mote in a sunbeam and the rotation of giant galaxies are controlled by the same conductor, by the same geometry. Many people tell me, Richard, science kills beauty. When you take a rainbow apart into wavelengths, it ceases to be magical. I never understood that. Do you really think that if I know how a flower works, what cells live in it, how photons interact with its pigment, it becomes less beautiful? On the contrary, I see more in it. I see not only the external beauty of color, but also the internal beauty of complex structure, and the history of evolution that created it to attract insects. Knowledge only adds layers of beauty. It never subtracts. It is the same with gravity. Before, you looked at the night sky and saw just lights. Now you look and see a great drama. You see the light of those stars struggling toward you through the pits and bumps of space-time. You see every mass in the universe reaching out to every other mass in an infinite, silent waltz. And the most amazing thing, this waltz happens strictly to the rhythm. It obeys rules. Think about this miracle. We humans can sit here, on a small rock orbiting an average star, and with a pencil and paper calculate what will happen in millions of years and millions of kilometers away. And the universe obeys our pencils. Nature speaks to us in the language of mathematics. Why? I don't know. It is a mystery. But it is a fact. And the fact that this language is accessible to us is perhaps the greatest gift we have. Yes, we still have questions. How to unite gravity and quantum mechanics? What is dark matter, which seems to add extra gravity where it shouldn't be? Why are the constants exactly the way they are? Some people feel uncomfortable when there are no answers. They want certainty. They want the correct answers to all the problems at the back of the textbook. But I can live with doubt. I can live with uncertainty. I think it is much more interesting to live in a world that we don't fully understand than in a world where all the answers are already given, and they are boring or wrong. Don't be afraid of not knowing. Don't be afraid to ask questions that seem stupid, because it was from the stupid question, why does the apple fall straight down, that the path began which led us to the stars. Next time you walk down the street, stop for a second. Feel the heaviness of your body. Feel the floor pushing against your feet. Remember that this is not just weight. This is your movement through time being interrupted by the earth. Remember that you are not just standing on a planet. You are traveling in curved space. You are part of this incredible, complex, breathing geometry. Gravity is not shackles that chain us to the ground. It is the connection that unites us with the entire rest of the universe. And now go and drop something, just to watch how it falls. Thanks for coming by. Next lecture's tomorrow. Don't be late.